In this video, we're going to continue our development of cool type checking with a discussion of type environments. Let's begin by doing some more type rules. So here's one for the constant false. So it's provable that the constant false has the type bool, and that's not too surprising. If I have a string literal, s, then it's provable that that has type string, and that's also not very surprising. The expression new t produces an object of type t, and the type rule for that is very straightforward. New t has type t. And we're just going to ignore self-type for now. As I mentioned in an earlier video, we'll deal with self-type later in a video all its own. Here are a couple of more rules. If it's provable that an expression E has type bool, then the Boolean complement of E, not E, also has type bool. And finally, perhaps our most complex rule so far, the rule for a while loop. And recall that the E1 here is the predicate of the loop. This is what determines if we keep executing the loop or not. And E2 is the body of the loop. And so E1 is required to have type bool. It needs to be provable that E1 has type bool. And we allow E2, the body of the loop, to have an arbitrary type. It can have any type t. It has to have some type, so it has to be typable under some rules. But we don't care what the type is, because the type of the entire expression is just object. We don't actually return, this expression doesn't return an interesting value, doesn't produce an interesting value, and to discourage people from trying to rely on it, we just type the whole thing as object. And this is a little bit of a design decision. Now, we could have designed a language, for example, where the type of a while loop was type t, and that you would get the last value of the loop that was executed. But the problem is that if E1, the predicate of the loop, is false on entry to the loop the first time, then you never evaluate E2 and no value is produced. And in that case, you would get a void value, which if somebody tried to dereference it, would result in a runtime error. And so to discourage programmers from relying on the loop producing a meaningful value, we could just type it as object. So far, it's been pretty straightforward to define reasonable type rules for every construct that we've looked at. But now we actually come to a problem. Let's say we have an expression which consists just of a single variable name, and that's a perfectly valid, cool expression. And the question is, what is the type of that variable? Call it x. And as you can see, when we're just looking at x by itself, we don't have enough information to give x a type. This local structural rule does not carry any information about the type of x. And stepping back one level, inference rules have the property that all the information needs to be local. Everything we need to know to carry out the function of the rule has to be present in the rule itself. There are no external data structures. There's nothing we're passing around here that's on the side. Everything has to be encoded in this rule, and so far at least, we just don't know enough to say what the type of a variable should be. So the solution to this problem is just to put more information in the rules, and that's what we're going to do. So a type environment gives types for free variables. So what is a free variable? A variable is free in an expression if it is not defined within that expression. So for example, in the expression x is free. In the expression x plus y, well, here this expression uses both x and y, and there's no definition of either x or y in that expression, so x and y are free in that expression. If I have let y dot dot dot, so I'm declaring a variable y in x plus y, well, what's free in this expression? Well, this expression uses x and y, but the use of y is governed by a definition of y that occurs within the expression itself. So we say here that y is bound. Y is a bound variable in this expression, but x is still free. So only x is free in that expression. And the idea here is that if I have an expression with free variables and you want me to type check it, you have to tell me what the types of those variables are. So I can type check x if you tell me what the type of x is. I can type check x plus y if you tell me the types of x and y. And I can type check this expression, this let expression, if you tell me the type of its one free variable x. The type of y will be given by the declaration in the let, but you still have to tell me what the type of x is. And so the free variables are just those variables where you have to give me the information, and then I can carry out the type checking. And a type environment encodes this information. So a type environment is a function from object identifiers, from variable names, to types. So let O be a type environment, one of these functions from object identifier names to types. And now we're going to extend the kinds of logical statements that we prove to look like this. And the way this is going to be read is that under the assumptions that variables have the types given by O, so the assumptions go over here on the left side of the turnstile. These are the assumptions that we're making about the free variables in E. So the assumption that, free variables have the types given by O, it is provable, that's this turnstile here, that the expression E has type T. And so this notation very nicely separates what we're assuming, this is input to our process of figuring out what the type is, from what we're proving. So if you tell me the types of the free variables as given by O, then I can tell you the type of E. The type environment has to be added to all the rules that we've gone through so far. So for example, for integer literals, if I have some set of assumptions about the types of variables, that doesn't really change, it doesn't change what the type is of an integer literal. Any integer literal will still have type int. And so in this case, for this particular kind of expression, I, we don't use any of our assumptions about the types of variables. Now, it's a little bit different with the case of a sum expression. So if I have the expression E1 plus E2, and I have some assumptions, O, about the types of variables, well, then I want to prove that E1 has type int, and I'm going to do that using the types of the variables given by O. So E1 might contain free variables, and I'll need to look in O to figure out what the types of those variables are. And similarly for E2, I will type E2 under the same set of assumptions. And if E1 has type int under the assumptions O and E2 has type int under the assumptions O, well, then I can conclude that E1 plus E2 has type int under the same set of assumptions O. And we can also write new rules. So now our big problem with free variables becomes a very easy problem. If I want to know what the type of X is, and there's a missing O here, if I want to know what the type of X is, I simply look it up in my object environment. So under the assumption that the variables have the types given by O, what is the type of X? Well, I look up in O what the type of X is assumed to be, and then I can prove that X has that type T. So now let's take a look at a rule that actually does something interesting with the variables from the point of view of the environments. So here is a let expression. And let's remind ourselves what this does. This is a let expression that has no initialization. So it says that X is going to be a new variable. It's going to have type T0, and that variable is going to be visible in the sub-expression E1. And so now how am I going to type check that? Well, I'm going to type check E1 in some kind of environment. And this is new notation here. So let me define what it means. So remember, O is a function. It maps variable names to types. And O, t slash x, this notation here, is also a function. And what this is the function O modified at the single point x to return t. So in particular, this function, this whole thing here is one function. This whole thing I'm underlining here is a function. That applied to x returns t. So that says that this set of assumptions says that x has type t. And for any other variable, if I apply it to some other variable y, where x is different from y, well, then I just get whatever type y has in O. Okay? So what this rule then says is I'm going to type check E1 in the same environment O, except that at point x, it's going to have the type T0. So I'm going to change just the type of x to have type T0 because that's the type of the new identifier that's bound in E1. And all the other types will be the same. And using those assumptions, I'll try to prove that E1 has some type. I will get a type for E1, and then that will be the type of the entire let expression. Now, notice something about the type environment. What this says is that before we type check E1, we need to modify our set of assumptions, modify our type environment to include a new assumption about x, then we type check E1, and then, of course, when we leave type checking E1, we're going to remove that assumption about x, that new assumption, because outside of the let, we just have the original set of assumptions O. And so I hope that that terminology and that description reminds you of something we talked about earlier, because this type environment is really implemented by the symbol table. So in our rules, the type environment carries around the information that will be stored or is typically stored in the symbol table of a compiler. To summarize this video, the type environment gives types to the free identifiers in the current scope. And this is very important because it doesn't even really make sense to talk about type checking an expression unless we have some information for the types of the free identifiers. And the type environment is just a way of formalizing that, of giving a name to some set of assumptions about what the types of those free identifiers are. Notice that the type environment is passed down the abstract syntax tree from the root towards the leaves. That is, as we pass through definitions, the type environment is extended with new definitions, for example, in let expressions. And so the type environment will grow as you pass from the root of the abstract syntax tree down towards the leaves of the abstract syntax tree. And then the types are computed up the abstract syntax tree from the leaves towards the root. So we begin at the leaves, get all the types of the leaf expressions, most of which are very easy. Things like integers and string constants have the obvious types, and we just look up the types of variables in the type environment. And then we compute the types for the more complicated expressions in a bottom-up fashion.